Am I streaming? This is the question. Looks like I am streaming. The problem is, am I able to change this? I am. Good. Programming a path tracer in x86-64 assembly, because that's how cool I am, is that I do that kind of thing, and then I am that kind of guy. As the stream suggests, as the stream title now suggests, what we're going to be doing today is we're going to be programming a path tracer in x86-64 assembly, or at the very least, continuing our work on a path tracer in x86-64 assembly. I've got a new window manager and all sorts of other shit going on today. I created a whole sort of a new setup for how I want to do development. So there will probably be some kinks as I realize that my entire central approach is incorrect. But I think that it should be the case that we should be able to sort of move along and work with what we have. We need to give it a chance. We need to give it a chance. What I have here is some Turkish coffee, some nice Turkish coffee, just with some espresso grinds, but it still works. Okay, so when I did this before, okay, so here's my new dev setup. I can just hit F9, and then all of these things pop up, and I've got, for instance, my trusty web browser over here, so I can say ASM, x86 instruction reference, because I am going to need that. And we're going to go to our Felix Cloutier, and here I go. And yeah, I haven't used terminal-based browsers very much, but I kind of want to see if I can get into the vibe, because I don't like my screen to be tainted. That's what they say. So yeah, if I say add PS, that takes me down here. Oh, and then I'm right here. So that's not bad. I can't use Vim commands here, which is kind of too bad, but that's okay. Okay. Well, I can play around with that. And then Z to go back. Yeah, that sounds good. Okay. Well, I guess we're getting on with it now. The girlfriend just took a lunch break, so I'm in communication there. So hopefully it doesn't take up too much of your precious time. Of all the people here. Oh, and then I can also hit F1, and then it comes up with a D menu up top there, and I can just do like the run make command. It looks through all the make commands, so I can just do that. Here's our renderer. I think our samples are probably set a little bit high right now, so we're running a little bit slow. I need to get an FPS counter up at some point. Usually I just go to render doc to check that out. But yeah, right now for samples, what do we have for samples right now? 16? Yeah, we don't. At 512, yeah, we're not going to be running at 512. I'm gonna be trying to go for a kind of a low resolution situation here. So like 256 by 256 is the planned target. Looks like I think this looks like we're at full FPS here. Right now we're doing 4 samples. It's just a simple diffuse texture, and then the background is just the ray color, the color of the ray that's being traced through the world. Whatever that ray ends up at when it intersects with the sky is then just is the calculation for that color. And so then we just have a single cube that the rays are tracing against, and they kind of have a random diffuse reflection off of the surface. Um, and you can see it's sort of colored red, white, or red, blue, and green there, because it's bouncing, and it's bouncing off into that sky, and so since the cube is oriented, it's aligned to the axes, and so is the ray colored thing. You get these perfect green, red, blue things. If that makes any sense to you guys. Okay. That doesn't close automatically. That's too bad. We'll sort that out at some point. Okay. So the thing that I wanted to work on today, because I think I had been working on some sort of performance stuff for a while. It's running in multiple threads at the moment. I'm on an 8-core CPU right now, so I just have 8 hard-coded for the thread count, but we'll get the CPU information at runtime at some point here. And then right now we're using SSE SIMD instructions, so we're doing all of the vector calculations with SIMD instructions, which is fun. Eventually I'm going to be moving to an AVX512 code path, so there will be 2 different code paths that it chooses at runtime based on the CPU. And for the AVX512 code path, instead of calculating, doing 4 calculations at once, or operating on 4 scalar values at once, it can operate on 16 scalar values at once. And so at that point, we'll have to complicate the algorithm, because we'll need to trace rays and kind of buffer operations of the rays based on the result of different calculations and stuff. So anytime that there is a branch that can't be trivially solved in the tracing calculation, like when the ray needs to bounce and then, trace, and that could be different for all the different ray calculations that we're doing, we need to then buffer that into a queue that's specific to that operation, and then the path tracer will just for every ray calculation, it will sort of work in waves, so it'll do all of the rays in its region, like the first bounce or whatever calculation, and then it will, based on those, it'll then go through the sort of the second pass, and then the third pass, and the fourth pass, and it'll do as many passes as it takes for there to be no operations left on the rays. This is sort of, I think, this seems to be the way that performance path tracing is done, and I can't think of a better way to do it. And I think we'll see. I mean, I'm really interested to see whether I can make it faster than the SSE code path, because the SSE code path is very, very simple. It's like almost everything is able to stay just in the registers, and there's almost no reads out to memory. We could even make that better. We could put more things in the XMM registers, because there's a few left over that we can use as of now. So it's very, very lean. And it's just just operating on the registers. But once we get to the AVX512 stuff, it's going to be like a whole different ball game. There's going to be a whole, we're going to need to be worrying about memory a lot more, and whether the overhead of our wavefront tracing scheme is worth doing, like, because really, if you can pack, I think you should be able to pack all of the rays, like the XYZ components. You should be able to pack them. You shouldn't need to pad them in 4s, I don't think. I haven't really thought much about this yet, but or looked at the instructions that I have available to me. But so you should be able to fit 5 3-dimensional vectors into each calculation. So it's like a 5x speed up. But is that 5x speed up going to be worth the overhead of storing the wave, of doing that? Yeah, I don't know. We'll see. Because it's going to be a pretty non-trivial amount of memory. Like, it might even make sense to Like it might even make sense to have certain threads being used for flushing the queue every now and again, and then like other threads being used for. Well, no, yeah, you just have. Yeah, I don't know. We'll think about it. We'll think about it. I don't. I guess I don't really see any reason to make it so that it really is just like the different threads. Each thread will work on a region of memory like it is right now. You know, they'll all operate like right now. They get each thread is assigned a sort of a region of the pixel buffer, and it just traces all the rays that for those pixels, and it's like a contiguous region of memory. And I think we should continue to do that because I don't see any reason that you should be mixing up that stuff. Yeah, because then you would be dealing with all sorts of stuff where, yeah, the different threads would be sharing memory that really doesn't need to be shared at all. It can just be totally segregated per thread, as it is right now. So that'll be good. I think that'll be good. The other thing though that's cool about AVX 512 is that it upped the register size to, or not the register size. It gave us double the registers, so we have 32 ZMM registers rather than just the 16 registers we have now. So that will make things better, I suppose. Like we can just these are points where I'm kind of reading memory directly from the data section, and we can just plop those all into their own registers before the start of the thing. Yeah, okay, so I'm talking too much. But what I want to do now, because right now, again, we have this diffuse texture, and that is not what I want to use going forward. It's interesting that when it resizes, it pauses up so much. I wonder why that is. I don't know. Yeah, kind of interesting. But anyway, right now it's a diffuse texture or a material, but I want to make it a metallic material. So first I'm going to do metallic reflections. It's going to be fuzzy metallic reflections. And then I will introduce sort of a refracted, transparent, glassy material, like a glass material. And then I'll mix the two. So it'll be like a fuzzy metallic glass material by the end. And then we will put a grid of these cubes, these like transparent glossy cubes in a voxel grid, and then you'll play Snake on it, and that'll be fun. And then everyone will think that I'm really cool once I've made that program. Okay. So again, we're working on now getting this into a place. That's too bad. Getting this into a place. I think I want that to actually just be the whole thing over here. So we want to get this into a place where we can be doing metallic reflections. So I'm just going to reference the canonical material here. I don't know how to select all here, but I'm going to do that. I'm going to say ray tracing in 1 weekend. The Peter Shirley thing, because that's going to tell us how to do the metal. I mean, it's pretty simple. We're just going to reflect it, but he'll have the fast way of doing it and stuff. Have I done it? Oh. Okay. Oh, this is kind of lame. This is pretty lame. Yikes. Why is this so bad looking? Does this need to be this bad looking? I'm going to instead Do I have like W3M? I do. W3M, okay, let's try that. How do I, can I do that? Okay. Ray tracing in 1 weekend. And we'll search. Oh, it's got pictures and everything. How about that? Oof, this is basically the same. That's kind of wild, dude. Dude, why is that so bad looking? God damn. All right, well, the dream is gone. And I have become, I have become comfortably numb. Ray tracing in one, ray tracing in 1 weekend. Plop that over there. Try to make it sort of the same size. Okay. Metal. We're going to make metal. And the metal is going to be really good looking. Okay. So, mirrored light reflection. So the reflected ray direction is just V, which is the incoming vector, plus 2B. What is B? Is B the normal? That makes sense, I suppose. Yeah. 2B. Oh, scale the normal vector by the length of the projection of V onto N. Oh, yeah, okay. Okay, yeah, that makes sense. Because V points into the surface and we want B to point out of the surface, we need to negate this projection length. Okay, so it's going to be V minus, yeah, okay. Yeah, minus, that's the negation going on. 2 times dot of the vector and the normal times the normal. Excuse me. Scale the normal vector. Yep. Okay. Okay, so where are we? So we need to comment out some code here. Where's our thing? So we have, okay, get normal of intersection. So we got the normal, so we need all this. Ah! And it's really weird that I have not commented that this is where the normal is. XMM8 is the normal. Oh. Okay, XMM8 is the normal. We don't need this anymore either. Okay, so then this is the diffuse reflection. Calculate hit position. What is that hit position? Yeah. Okay. Yeah. Which we want. Okay. Which is the new origin. Origin of our next ray. Ah! That was a loud sound. So it's really just this tiny little piece that we're not using. So let's say, let's do this. I'm going to say, does FASM have like enum? Like enums? Enum. Okay. Macro enum. Yuck. Okay, whatever. I'm just gonna do this. let's say 1 diffuse 2, let's just do 0, starting at 0. I just want to create a little so that we can decide on the code path at run time or at compile time here. If 0, else if 1, okay, cool. And then, oh, no, not if 0. We want to say material mat equals 0. Okay, and then we're gonna, well, no, oh, this is pretty lame. Okay, the dev setup is very brittle, I will say that. Like if things get screwed up, then they really get screwed up. Okay, so where are we again? We are up here. We are up here. Yeah, if 0. Okay, if material equals 0. Okay, so that's working. If material, let's say material equals 1. Okay, cool. Doesn't do anything. That's a nice default. I didn't. I guess that makes sense that it would end up that way. Okay, so because the direction. Oh, I wonder actually why it ended up that way. Ray direction is the Lambertian. How do you pronounce Lambertian? Lambertian? Now I'm on video, so I have to like pronounce it correctly, right? How to pronounce Lambertian? Lambertian. I don't know if that's true. Anyway, so here we go. So now it's time to do what we want to do. And what we want to do is this. Calculate metallic reflection. And it'll be fuzzy eventually. We're going to pop that up there so that we know. Okay, calculate. Come on, what are we up to here? Calculate diffuse reflection. My hands are cold, which is a problem. Very big problem. Okay, so so this one, okay, yeah, was like just getting a random distribution there, whereas this one is going to do this. So let's reflected vector equals v minus 2 times the dot of v and n times n. Let's say 2.0 because that's clearer to me. So we have our vector. So right now we can just construct that this bit here, and then subtract the vector by that. And the vector itself is is XMM7. Or no, it's XMM11. I see. Yeah, I wonder why. I wonder why we're not just using XMM11 to start with here instead of XMM7. So let's replace that and see what happens. And then, all right, it still works. I don't see any reason why not to do that, so I am going to do that. Yeah. Yeah, so XMM11 now is the new XMM11. XMM11 is the new direction. So, and then XMM11 is currently the direction as well. Okay, so let's do the dot product first, and I need to remember how to do that. I have it here. DPPF is the thing. So 11111111111. Yeah, I would say I think that's just saying do all of the calculations and write all of the calculations out into all of the numbers. Okay, so okay, yeah. What is this local stuff about? Oh, yeah, gotcha. So it'll be, again, the vector, and XMM1 would then be the dot product. So do we need the normal? Okay, we're going to need to use the normal. Let's grab. We're going to need to use the vector a couple times. Let's start with the normal. Let's see if we can get away with the normal here. So XMM7, and that'll be XMM8. So XMM7 will be the normal. I've never done that before. I'm just going to do that. Okay. We're going to do XMM7 against XMM11. Dot of VN. And then we're going to, well, I guess we're going to multiply that by, by N, by the normal. XMM7 will then be, multiplied by the normal, which is XMM8. Yeah? Yep. Yeah, and that'll be 2.0. Okay, and then we need to, no, we don't have the 2.0 yet. Times N. And then XMM7 DQ word. I think we have V4 2. And then we want to subtract the, this is pretty easy. So XMM11 sub PS XMM11 XMM7. XMM7 reflected vector. No, not 7. 11. Is that it? For real? Oh, yeah, okay. Yeah. That's fine. Okay. We didn't put in the dot product mask. Yeah. Okay. Yeah, anyway, whatever. Okay, that's probably correct. But in order to know if it's correct, I think we need to. I think because right now, when I'm calculating the ray color for the background, I'm using the absolute value. I bet you maybe that ends up just being the wrong thing. Okay, that looks pretty good. Let's go ahead and make that go slower. Theta per second. I want to be 1. So we're looking down on it. So green is at the bottom Y, and so green should be, yeah, there should be like a gradient down to green at all times. Yeah. It's interesting that there's that screwed up bit at the edge. Like I wonder if there's moments where it's only on that on these two. It's only on the two that are facing towards the negative direction. That there's this line that's black along the edge. Other than that, I think this is a correct metallic situation we have going. I do want to do this other thing that I did because I find it pleasing, and I'm interested to see what it looks like, which is I want to see because I've done this, and I think it's cute. DQ word. If you just kind of double it, then it creates a... Ooh, that's not doing the same thing at all. Oh, I wonder why that is. Ooh. Yikes. Okay. I wonder if maybe I should do that here. Oh no, 255. Oh, I see. It should be 2, not 255. Okay, yeah. Okay. That does something pretty cool. Dude. I really like the metal. It's too bad about that thing on the corner. I wonder why that is. Pretty cool though. It's pretty cool. What happens if I up the samples? Does that end up being? Oh, first of all, let's bring the samples sample count. Okay, I should use this second window to go other places and then try to stay in the same spot when I'm yeah. Anyway, let's bring the sample count to 1. Okay, that turns out, yeah, just about the same, just without the anti-aliasing. Does it have the black? I guess it's hard to tell. But okay, yeah, it doesn't. It doesn't have the black thing, which is kind of interesting. I wonder if it could have to do with the way that the stuff is being averaged out. Like maybe. Again, I don't know why that would be happening just on the corner, but like, could there be a situation where we should be clamping the value of the sample? Yeah, probably. Yeah, I mean that's probably it. We should probably be clamping the value of the sample when it hits the thingamabobber. Oh God, I need to get that to do that automatically. Okay, so we've got the reflective vector, blah blah blah. Okay, let's up the sample count. Let's make it 2 and see if it shows up. It probably will, I would imagine. Oh yeah, there it is there. Oh, that's actually not facing yeah, that's not facing the black part. up the samples here. Probably the thing about upping the samples on this particular thing is that it doesn't really need extra samples other than for anti-aliasing. Yeah, so there even on like here, there's like a on this edge, there's an edge which isn't quite the same as the others. So it's hitting the corner and actually doing something about the fact that it hit the corner. Which is strange. I guess could we have a situation where the normal that gets calculated is there's like, because right now the normal should only just be in one of the 2, 3, 4, 5, 6, 6 directions, the 6 axis aligned directions, and so it could be that the way we're calculating it, that on the corners it ends up having 2 of the elements, and it isn't being normalized, so I don't know exactly what that would do. In the negative direction, I suppose that could do funky things. Let's just normalize that vector for now and see what happens. So so that's the normal, and we'll say v3 norm. v3 norm. Is it like that? Oh, it is. Okay. Okay. Has that done anything? All right. We still have the black pixels here, and the green here. It's interesting. It's the green. It's green there. I don't have an easy way of testing the magnitude of a vector, because what I would do here to debug this, if I had that quickly, I might do it anyway, but is check the magnitude of the normal and just exit if the magnitude is not, within a very small, within essentially equal to 1. We have this intersection code, and I know there was something that I did that was kind of not wrong, but well, wrong I suppose, in that I Inigo Quiles Ray. I took the ray intersection stuff from here. Intersectors. Okay, so what I did was RO inside the box, RO outside the box. I didn't do anything about that. No intersection. Okay, so yeah, one thing that I did not do is all I did was I checked if this was, if T near was greater than T far, T near below, if T near is greater than T far. Oh, that's interesting. What am I doing here? Oh. Oh, okay, yeah, that's interesting. Okay, yeah, sure. T far. Oh, I should be, I'm testing the wrong thing here. I just realized. I should be testing, T far. Let's do that real quick. if t far is less than 0. Alright, that didn't do anything. Didn't do anything we weren't already doing. I also wonder why I'm testing for epsilon instead of actually 0. Honestly, it just seems like a waste. Like, I don't even know if I need to do that at all. Let's see. Looks like I don't. That would be, okay, return vector 2 is -1. Yeah. Yeah, totally. Let me comment that so that and then we are multiplying by the negative sign of the redirection. See if we can detect this happening with the diffuse material. Oh, jeez. There is kind of a funky pixel there, I will say. Let's bring back the absolute value here. Why are we too bright? Oh, because of the... oh, okay, well, hang on one second. Yeah, I got rid of that before. Okay, so, wait, whoa. Yeah, before 2, yeah, we don't need that. Okay. Alright, anything funky? Anything funky? That doesn't look bad. That doesn't look bad. That doesn't look bad. Did I already check that side? Well, it should be, yeah, 1, 2, 3, 4. No, that doesn't look bad. Okay, okay. So we're good there. Okay. Do we have... I don't know what a good way to clamp a number is. I don't know if there's like an instruction for that already. Jesus. Yeah, okay. Clamp XMM register. Ugh, where... Okay, x86 assembly, reference. Thank you. There is no clamp thing. Do we have a... We don't have a situation where we've clamped something? Okay, so what clamping is just... Yeah. Okay, well, no, we don't want the absolute value either. We don't want the absolute value either. Yeah, well, yeah, that's the thing, is that Okay, let's go back to the metallic material. Oh, well, there's no weird stuff going on when we don't do this multiply by 2. So that could really be all it is, you know? Wait, how did we get that? How did we get that? What did we do? Right, the absolute value stuff. Okay, so then does it come back with the, when we don't multiply by 2? I think it does, doesn't it? It does, okay. It is still here. So, so then what we want is, what was I going to try? I forget. Okay, not clamping. I was going to try... oh yeah, I was going to try setting the bounces to 1, like the maximum bounces. Okay, so it's not bouncing around too much in there. Still doing it. Still doing it. All right, yep. Did that just end up being the same as the background? Yeah. Yeah, that makes sense. With no bounces. Okay, so it's not the bounces. It's not bouncing too much. Calculate hit position. Okay, that's not going to be our problem either. What is normalizing doing for us here? Ooh. Interesting. There's an interesting aspect to the not normalized version here. Yeah, I guess it makes sense that it would be different because we've got a camera that's pointing out to a viewport that's flat and it's not curved around the camera, so the rays of the edges are longer than the rays of the center, and so the edges, I think we can see that the edges are getting, there's like a gradient from the edges to the center of differing brightness. I'm not sure if that's actually true about what we're seeing, but that's what I would expect to be there, and it doesn't look that wrong. The adding to the sum is happening. Is it possible that we only want to add when it is above above 0, or like that? Is it possible that we want to clamp everything? Hmm. Interesting. That's a cool instruction. Very cool. Ah, okay. It would be a min. Oh, yeah, yeah, yeah. Okay, or a max. A max. Max. Let's try that. So right now, where are we adding the? All right, we're adding it to the color sum. So let's go with max PS XMM 14, which of course is being used as the color. XMM 4, no, XMM 8 is the color right now. And then we want to do DQ word V40. Okay, that fixed it. It fixed it. It did feel like that was something. I should probably think through what exactly was happening there, because it does mean it does mean that the normal was off on that corner. Okay, sorry. I know what it was, I think. I know what it was. It was the colors were canceling each other out on that corner because half the samples half the samples would end up on one side of the pixel, and half the samples or of the edge of the box, and one half of them would end up on the other side. And it just so happened that on those particular edges, one side resulted in a positive value for some color channel, and one resulted in a negative color value for one channel. That's also why we had that green strip, is because that was only for one of the channels, whereas for those other corners, it must be for all the channels, and then those two samples would cancel each other out. And that makes sense. That makes total sense. It really does. It makes total sense. Let's try this multiply by 2 again, because I like the way that looks. Yeah, it looks all cute and fancy. Its name is Boxy, I believe. People usually say. Let's go Q render doc. Where's our memory going? 86. That's not bad. That's not bad. Okay, what are we at right now? 34 FPS. For what? For 64 samples? That's a pretty good amount of samples. There's our better samples. That still doesn't look like actually it's full FPS, which is kind of crazy. 82? So yeah, it's getting there. It's pretty cool. Pretty cool. You know, what's too bad is that adding the fuzzy metallic material is going to do, like, possibly nothing. No, it'll do something. It'll do something, yeah. So what happens if we switch to, like, 4 samples? Because actually it's kind of abysmal that we're already at such a low... so slow. That's kind of crazy. You know, it's kind of crazy. Do we have oh, we did. We had one running. Oh my god. Somewhere in the background. It still doesn't fix it. Maybe it did. I don't know. Let's do it again. Make sure. I think the way that I might be dispatching these from the thing is might be fucking with the... Well, no, it shouldn't be. I don't know. The multi-threading still leaves dangling tails for some reason, perhaps. Okay. How big is our stride? Times 8. All right, let's say let's make it smaller. See what happens. Oh, faster, faster. Not much, but a little bit faster. It's very variable. I'm you know, I wish it wasn't so variable. Okay, so cool. Let's do one sample, and I sure hope that's fast enough. It better be, you know. Dude, we should have no hiccups at all here. On one sample. I mean, I'm targeting 60 FPS, but like, this is crazy. Like, one sample. What does 16 do? It's weird. I wonder why the sample. Oh, it kind of makes sense that the samples raising the samples might be, you know, not doing as much of a thing as it should be. Like, this is 16 times the workload, and we're only losing like 10 FPS. So I guess like, yeah, it's like the more work that we do, the really like more work is going to scale well, I think, is the moral of the story here. So hiccupy though. I wonder what happens if we switch the thread count to like 4. Dude, is it gonna go faster? It could have just been because QRenderDoc is kind of screwing with us here. I'm just gonna keep this around. We're gonna move this over here. Okay, still at 99 at 8 with 8 threads. What happens if we... So thread count is 1. Let's go up to 64 samples. Okay, very slow, very slow. Okay, so it's just QRenderDoc that's running badly here. Okay, so 11 FPS. And then let's do all 8 threads. Build, I just want the regular thing. Okay. What were we running at before? Something very low. 37, 40, 40. Let's go back because I don't remember what we were running at. Let's see. We were at like 40, 11. So it's like a 4x-ish speed up. A little bit less, 3.8, 3.7. Okay. Okay. Well, that's good. I mean, you know, that's like, it's like, you know, 50% of the maximum that we could expect from multi-core, which is pretty good, you know. I mean, that's pretty good. Let's go to 16 samples, because 16 is kind of a reasonable thing to target, I think. IMO. Make sure, okay. Maybe 16 is not a reasonable thing to target. How many cycles does the dot product instruction take? Like, let's just get rid of that. I don't know what that's going to do to the way it looks, but let's just get rid of that and see. Oops. okay. Oh, we're doing pretty good here. 67, 59, 78. I would like to know, because now I don't remember. Again, I need to like write these down and shit. Build. Okay, well, never mind then. Never mind. It's just being weird. So what do we have for our samples then right now? We're at 16. Maybe 8. Poof. It's being kind of weird. Okay. Just go like that. Let that branch predictor do its work here. That's probably pretty stable. At some point, I'll automate this process and you know, graph it and stuff. Okay, so again, we're like sort of between 75 and 95. I wonder why it's so variable. Kind of obnoxious. This runs much better on my laptop, which is a 12-core AMD processor. Oh, hello. Hi. Yes. Well, I suppose I can just talk to you directly and say, I can trace... oh no, I can trace your paths. I can't path your traces. But you know what I can do is exactly what you would like me to do. Okay. So anyway, I think that probably the dot product there was doing a slight bit of something, but not anything particularly major. And you know, we still got lots of performance left on the floor. We still got lots of performance left on the floor. We haven't done our AVX512 instructions. We haven't. Oh, I'm actually curious as to whether this does a thing. 96. Man, oh my god. Very interesting. 97, 96. There's something. There's something going on that's giving us incredibly variable performance characteristics. Because even on 128 by 128, okay, okay. It's much more steady on the AMD CPU, which makes me think maybe the way that the OS is scheduling the threads is kind of screwed up, and maybe we shouldn't go 8. Maybe we shouldn't do 8 threads. You know what I mean? You guys know what I mean? Yeah, vector mathematics. It's something special. It is something special. There's something about it that that just projects my buttons. Okay. All right. Okay. So when we do all 8 cores, performance is worse. How about 7? Well, let's do 256 so we can get a good baseline here. Or the CPU is just a little bit colder than it was a few seconds ago. It's one of those things. $100. Okay. Okay. Wow. Okay. I guess that's not that surprising. Let's do lots of samples. 64 samples, please. That ought to do it. There it goes. It's hurting now. Okay, 48, 45, 48, 50. Well, let's confirm. Let's confirm the thread count thing. Yeah. Slower. Slower. It's slower. Faster. About as fast as 6 cores, which, you know, you would expect, obviously. So 7 cores is maybe even 6 cores is the sweet spot. I don't know. We'll graph it. We'll graph it later. We'll graph it later. I think we're doing good. I think we're doing good as is. We want to implement fuzzy reflections. We want the reflections to be fuzzy. And in order to do that, what we're going to do is we're just going to add a unit vector. Yeah, a random unit vector, which I think we have a thing for that already. We're going to add a random unit vector to the reflected ray, and then scale it by a fuzziness factor. So let's define a fuzziness factor. I think what I'm going to do, just so I can see you, is pop you out. I'm gonna pop you, baby. I'm gonna pop you. Are you still here? Oh, you are. I'm gonna pop you, baby. I'm gonna pop you. I'm gonna pop you like a. I'm gonna pop you like a. You know. I think you know. There you are. You're popped. Get popped. You know. Okay, where was I? What was I doing? Okay, so we want to define a thing for that. What's the best place to put that? Probably. When will it be used? At the end of these constants. So we should probably put it like right there. You've been pepped. You've been pepped and pooped. Well, actually, let's see. Let's be serious about this and go to where our calculation occurs, and it occurs right here. And we've just used v42 gets used. That should actually be up there then. Where is albedo? Albedo gets used. Where is our albedo? Attenuate color from bounces. Oh, XMM9 is just being where's that get put in there? Attenuate. Oh, okay, it gets attenuated up there. Okay, so then we get the sign mask. Up there we have one being used. 15 seconds stream lag. Fair enough. You know, understood. Thanks for telling me. 0. Let's put 0. These are going to be fine. We're going to get a cache miss on pretty much all of these anyway, so it doesn't really matter. But, yeah. Ugh. My God. $256, yeah. 256 kilobytes. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 times kilobytes? Oh yeah, that'll be just fine. That'll be just fine. Fuzz factor. Let's make the fuzz factor something like, I would say 0.1 makes sense. The cube is about 0.5 units across. 0.1 might be kind of wild. Let's do it. Let's do it. And then I assume we also need to normalize the reflected ray, but I think we're doing that. We're not. Do we care? Do we care? Yeah, if we add a unit vector to an array that is of varying size, then the fuzziness will be less proportionally to how long the array is. So that being said, is the array already normalized when it's coming in? I don't believe it is. It does seem like a lot to, normalizing this seems like a lot, I'm going to be honest, but that's okay. We can always look at it later. Normalize, if we don't normalize, fuzz factor will vary by array length. Test it once we get there. Okay, and then we want to add a fucking unit vector. I think it's this same exact calculation here. So let's just do that. Frand, blah blah blah. Why are we shuffling? My tummy is growling. Why are we shuffling here? I should have commented this part. Frand normal, frand normal. Oh, I see. We're just broadcasting it to all of the lanes, and then we're blending. Oh yeah. Got it. Okay, cool. Yeah. And it needs to be normalized, yeah. Okay, so we're basically just doing the same exact thing to the metallic reflection that we did to the diffuse reflection, except except it's just a unit vector. But that's what. Oh no, yes, makes sense. Yeah. That's how we were getting a. Okay, it all makes sense. Okay, so what is XMM11 in this case? XMM11 is the ray direction. Okay, yeah, sure. Okay, so we shouldn't use XMM11 here, I don't think. So let's do XMM. Yeah, let's do XMM. We can just reuse 7 now, I think. And 6 and 4 are usable. 6 and 4 is usable. What did we do? 11. 7. And then we want to add 7. What is 8? Yeah, 7 to 11. Does that work? We didn't add a fuzz factor, but that looks like it's the right thing. It looks like it's the right thing. So that's mul PS XMM7 by DQ world V4 fuzz factor. Okay, it's too bad. I need more. I need more cubes around to really see if this is working. It looks right. Yeah, it's just like a slightly diffuse metallic texture. I wonder if there's anything more interesting than the ray color I can project onto the sky without too much trouble. I can probably do, I can do like, not the full ray color. I can just do, you know, yeah, I could just like, yeah, shuffle the, yeah, let's do that. Let's do it. Why not? Let's say sample color, XMM8 is our current normal. Yeah, okay, XMM11 is currently XMM8. Okay, gotcha. Okay, so let's just broadcast. Let's chef PS XMM8, XMM8 from XMM8, and it will be 000B. Does that work? Whoa, that's pretty cool though. Whoa. I don't really know what's going on there. I think I might have been broadcasting the alpha channel, which is kind of wild. Whoa, dude. Or no, I should be broadcasting, what if we do 3? Oh, yeah, totally. I can't do that. Yeah. Wait, yeah, chef PS. How do we broadcast? It's going to be an IMM8. Selects a single prison for using 2-bit control. Yeah. Okay. Wait, 2-bit control, yeah? 2-bit control. 2-bit control. So we want to do... Let's try 0 for now. All 0. Okay, that does the same thing as before, which we could have expected. Stop it. What if we do all 1s? You know, okay, the thing is, this should work. Man, interesting. Maybe we should do this shuffle later on. That could be, to be honest. Add to color sum. Yeah, let's just do it right there. What does that do? Oh my god, why actually? Why actually? That doesn't make any sense. Unless I've got this bit mask wrong. Each 2 bits in the IMM8 byte, starting from bit 0, is the select control of the corresponding element of a 128-bit lane of the destination to receive the shuffled result of an input quadruplet. Select control of the corresponding element of the destination. Yeah. Yeah. Next 2 elements receive shuffle results from the blah blah blah. Packed interleaved shuffle of quadruplets of single position floating point values. Yeah. Interleaved results. Am I thinking about this wrong? Honestly, I do not believe so. I suppose, yeah, I mean, I suppose the initial number was normalized, like the sample color was normalized before, so, okay, so we need to do this. We need to do it before normalization. That doesn't work, crazily enough. Alright, well, anyway, I'm not going to deal with that right now. I'm confused as to why that's not working. Anyway. We do have our multiplication by 2 happening, which is fun. Does that make sense? Yeah, that makes sense. Yeah. It looks so much more uninteresting with the absolute value now. I gotta see maybe how quickly I can, how quickly I can introduce like a separate cube, because that's gonna do it. You know, that's gonna be sex on ice. You know what I'm saying? You know what I'm saying? Let's just yeah. Let's do that. Let's do 2 cubes. 2 cubes. 2 cubes. 2 cubes is gonna be, let's first of all push what we have. Right, now we want to, yes, implement 2 cubes. 2 cubes now. Trace array. So, where are our cube things being? So it's right here. Basically all of this. So we're trying to find T2 and T1. Excusez-moi. We want to find the nearest T-near. So in addition to XMM4, which will hold that, we also need to keep track of. Yikes. Okay, so how many XMM registers do we have available? We should really just free all of these up so that we have them. So 12 XMM 12. Yeah. Okay. We're going to free all of these registers. Because who needs them? Well, we don't need them. V4 pixel delta. It might get a little slower, but probably not that much, you know. Did I say V3? V4. Delta V. And then XMM15. Look from. We do use XMM15 all the time, so maybe we should just keep that for now. It's probably actually quite worth keeping that in the register. Okay, so XMM12 will be what was it going to be? T near T. Does what I'm saying make sense? I think it does. Where's our multiple spheres? What's our multiple spheres? Okay, multiple spheres. Where's our ray color? Yeah. World.hit. Where's our world.hit? World.hit. Oh yeah, in fact, he's got 2 spheres right here. List of hittable objects. Hit anything. Closest so far is ray Tmax. Yeah, that's all we need. So let's just say closest T. And the closest T once we determine that we have intersected, if t near is less than t far, if t near is less than t far, then we intersected. So let's say, well, let's do a different one. Let's now say if t near is less than t closest. Ignore. XMM4 is our t near, and XMM 12 is our closest. And let's also say cube. Let's make this the cube offset. XMM13 is the cube offset. Okay. Well, it should be the ray offset, but that's fine. Ray instance offset. That's a bit of a confusing name. That's okay. T near is blah blah blah. XMM12, and we'll say if we are if t near is if it is above okay, well, we can actually throw this up here as well. Yeah. I think. I don't see any reason why not. If we're above that, and then we should throw this up here as well. Trace ray. Okay, right. So where did this get? Yeah. Ray instance offset. When we trace a new ray, these then become different as well. So those should get put here. Test intersection is the thing now. Okay, I'm gonna have to write these registers out differently at some point as well. Yeah, let's go XMM12, closest T intersection. We are calculating, by the way, 2 points along. We're doing an intersection test. I don't know if you're actually watching or not, but we're doing an intersection test between a ray in the world, bloop, and a cube in the world. And in order to test that, we basically test. So if you have a ray, unless they're perfectly parallel, if you have a ray and a box, let's say in 2 dimensions, and you trace the and you try to see about an intersection between the ray and the box, then you end up with 2 values, which is the t value, or the time along the ray, which is how much you need to scale the ray to get to that point or whatever. You have the near value and the far value, where it intersects with the box first and where it intersects with the box next. And you basically test by each dimension of the cube, and you get basically whichever t value is closest between all of those dimensions, and then if it turns out that if the far value is less than the near value in your intersection test, then you are not intersecting with the cube, because you're instead you're like intersecting with this adjacent thing. There's good graphics that make it clear, but so right now we're going to now test against multiple cubes, and in order to do that, we're going to keep track of what that near t value is for each intersection, unless there was no intersection, in which case we don't update the value. Well, we only update the value if it's closer than a value we've already stored. And so in fact, I need to initialize the closest t value to something that, to something that we should initialize it. Okay, we've initialized it to 0. That's actually good. But anyway, so then we find the closest one, and that's the thing that we intersected against, and then we do our calculations on whatever the nearest thing we intersected with was. We're going to set the t value to 0 at the beginning, so then if it turns out that it's 0 by the time we've traced all of the different boxes, then we will just say that we didn't intersect with anything. Because if it's less than 0, then that would be behind the camera, and we don't obviously care about things that are behind the camera. We actually didn't have a test for this before about things that were behind the camera, so if there was something behind the camera, it would have showed up, but there was never anything behind the camera, so it didn't matter. But now we just get that for free because we have to test against something. Okay. XMM13 is the ray offset of ray per cube instance. Yeah. So then every time that we test an intersection, we will just add add PS. We will add like 1, let's say. We'll do this better later, but we'll just add 1 to the position. So offset of array, we will add, let's just add, yeah, v41. And I don't think it'll be a problem that our w coordinate is not 0. That's the hope. Yeah, that's interesting, actually. We'll see. Yeah. I don't think that will be a problem. So the ray direction is now XMM11. Or no, not the ray direction, but the ray origin. And the ray origin before was the ray origin. The ray origin. You know, we actually don't even need to calculate. We don't need to keep track of the ray. Yeah, we do. Yeah, we do. XMM15 is the ray origin. Well, XMM10 is actually, I think, yeah, the ray origin. Yeah. So we only need that for this point here. Well, okay, so I guess that's I guess we're good then. Yeah, we don't even need the current ray origin to be stored. Following registers remaining stable and updated on every bounce. Huh. Oh, God. Okay, I see. We need to keep track of what the origin is for the bounce that actually hit something, I think. No, we don't. No, we don't. Because it just gets overwritten. Yeah. Yeah, just gets overwritten. Gets tested once, overwritten after that. So then we don't need to keep track of it separately. Let's just say, now let's go up here and make sure that we note that XMM13 is free. How come, why is everything fucked up here? What's going on? Oh, geez, what's happening here? Two, three, four. Oh, yikes. All right, that's kind of yucky. Okay. Got it. Right. Okay. Okay, so we're adding to XMM13. Not XMM13. We're adding to 10. XMM10. Add offset to XMM10. Let's do that before we switch back to test intersection. Oh, can we do that invariably though? No, we cannot. We cannot. We cannot. So let's do this instead. Let's sub PS. Let's just sub it at the beginning. Subtract 1 from offset so that we are at the origin. At the origin on the first pass. Okay, so we've added the offset. And then we need to do all of our things, and the things have all been accounted for as far as I can tell. So then we just need to see, oh yeah. So then if t near is less than t closest, then we would like to go back to test intersection. Test intersection. If it's less than the closest. Yeah. Yeah, that makes sense. Yep. Because on the first thing, that would just not be there at all. Okay. Should I check here as well whether we are currently done all of them or not? Okay, let's jump to end intersection. Yeah, jump to end intersection. We don't ever use XMM5 here, do we? We do? Oh yeah, XMM4 is what we don't want to do anything with. I was doing 4 for no reason here. Okay, so XMM4. Okay, cool. We don't use it again, which is good. So once we have tested whether it intersects, we already know that it's closer than the closest. We already know that it's closer than the closest. Move APS XMM5. No, we're moving XMM5 into XMM 12. Okay, and then we want to end the intersection. Track closest T near. And then at the end of the intersection, we want to say compare. Well, we'll need an index here, I suppose. We will need. Yeah. Okay. I wonder. R9 reserve. Let's do R9. Let's do it. Cool. So then in order to trace the array, we need to, hello? Are we good? God damn it. Hello? Weird. Okay, in order to trace the ray, we need to... yes. We're going to need to XOR R9 and R9. Because, well, let's do R9D. I don't know. Whatever. 0... fuck. 0... in object trace index. Okay, and then this offset will come from that eventually. So, but for now, we are just hard coding the intersection. But that's actually nice. It's going to be trivially easy to calculate the offsets. It's just going to be, you know, it's just going to be the modulo and the division and the other things like this based on the index. Okay, where are we? Yeah, if we're smaller. Well, yeah. 4 is far, 5 is near. Jesus. I should really make this the same. So 5 is far. No, yeah, 5 is near, 4 is far. T near. If it's below. Oh yeah, if it's above, then we calculate. No, in fact, where could these myriad paths be leading? You know, there's a very well-defined calculation you could probably make to figure that out. But you'd have to read the source code. Okay, so but right now we are jumping to calculation before, rather. What were we doing? We had right now we had 4 and 5, which is far and near. We were saying if far is less than near, we did not intersect. Yeah, and that makes sense. So now we want to say instead if yeah, so okay, near 4 and 5, then there was no intersection. That's really what we want. Otherwise, we track the closest T near. Okay, that's good. That's good. I think that's all correct. So then we're going to compare R9 to, like, let's just say 2. Well, we're not just saying 2, let's be honest. We need to increment R9. So we're incrementing before we compare. Yeah, so, which, I guess that's weird that I've been doing that, but we'll just switch. We'll not do it for now. Test intersection. I feel like that might be it, but I'm not sure. D keyword v41 363. Oh, shit. What is this? Was this a stray copy that I didn't mean to do? I think I'm going to assume that. Okay. Okay. So we have an endless loop somewhere. So let's figure out why that is. So we are testing the intersection, blah, blah, blah. Ending the intersection, blah, blah, blah. Yeah, when we end the intersection, we increment R9. And if we compare R9... Are we XORing R9? We are. Okay, let's say I don't know why I'm testing if it's equal. I should be testing if it's greater than that. Yeah, if it's greater. If it's greater than 1. Oh, ha! I see. Whoa! That's pretty cool, though. Whoa. That's some wild shit, dude. Hmm. The paths don't go on forever, fortunately. Oh, but it was an endless loop. That's true. It's not that the paths go on forever. It's that the paths were intersecting. They were checking if they were intersecting with objects forever. So, you figure that one out. Okay, so without making it fuzzy, that's what happens, which is quite a peculiar result, I have to say. Did we check? Did we check if? Did we check if we didn't intersect with anything? Oh, okay, well, if we did not intersect, then we don't want to jump to calculate the sample color. Okay, hang on. Don't jump to sample, jump to intersection. So then we want this to be the same basic idea to happen. Where do we want it to happen? Multiply negative sign direction. Calculate head position. When do we want to check? We want to check if we didn't intersect with anything eventually. When do we do that? Okay, we do that right here. Check if... I guess we need to say check if XMM12 equals 0. Hopefully I can do that. What is with this shit? Oh my god. Okay, it's good. We're good. Okay, check if XMM, what was it again? Jesus. XMM 12 equals 0. I really hope that we can do this without needing to test it against an epsilon. Okay, jump if equal. If it's equal, then we just calculate the sample color right then and there, dude. Really? Invalid size of operand for uCommas? Oh yeah. Yeah, that's fine. Yeah, it just should be a D word. Whoa, okay, all right. So it doesn't think we're intersecting ever. 12 is the closest intersection. Are we updating it? Is being updated XMM5. We don't need to. We don't need to get epsilon involved. The thing is, we should not need to get epsilon involved. Just to be clear, because it should be bit. The precision should be bit perfect because we've XORed it to 0 all across. So there's no calculations that have occurred on it. If there are calculations that have occurred on it, then that means that t near was calculated at some point, and then in which case that is not the case that we would need to be checking for. So don't worry, buddy. Don't. So what are the E flags that get set? ZFPFCF, unordered, greater than, less than, or equal. All right, let's check if we ever jump host exit. Yeah, let's check if we ever get here. Isn't it called host exit? Am I wrong? Exit. Oh, it's exit and exit child. I had it backwards. We want to jump to exit. Segmentation fault. Interesting. That's odd. Oh, probably because we are a child in that case. Oh man, we can't just exit for our thing now. Can I printf? Okay, printf. Move. Where's our thing? Okay, so it should be just RDI. Message. Oh, but do we need to add like the message length? Ugh. Print here. I do it up here, I think, so I should be able to tell. Fuck off. Why are you telling me this? Printf. Move REX to 3. Yeah, debug message, call printf. Yeah, we're good. What? Ah, fuck. Okay. Okay, so we want to move message to RDI, and then we want to call printf. And that's if we make it to that point in the code path. Seems like we already did, but I want to make sure that that's true. Let's define bytes. Reach the point You're exactly right. You get it. This guy gets it. This guy gets it. Is the printf causing us to seg fault? What's that all about? Printf seg fault? Oh, what do you mean printf seg fault? Printf seg fault. It's 10. It's 10, right? Where's our message? Where is it? Tell me where it is. Let's align this by 64. Why not? Maybe that'll help. Right. Okay, that did help. Okay, but oh no, that did not help. We're still not. We commented out the print. Okay, we seg faulted still. I don't know why there would be a seg fault. Why there would be a seg fault. Printf x86 assembly. I put in a new line. It's doing message. Yeah, doing message. Come on, just show me. Just show me. Please. Oh my god. Yeah, that is more foolproof. Let's just do that. Ah. Should there not be a 0? I guess that's fine. There shouldn't be a 0. No, because it won't even reach the 0 anyway. It doesn't matter. Move. Okay. I'm moving the memory location of message, not the actual message. Not the actual message. So we want to say D word, Q word. Does that work? No. It should be. Yeah. It should be yeah. Should be. Call printf. Does moving RDI is RDI something we need? No. Okay. I just want to print out something. You know, it shouldn't be that hard to do that. It shouldn't be that hard. It shouldn't be that hard to do that. Maybe just like calling printf from a different thread doesn't get printf from child thread. Seg fault. No, it's not what I want. Well, yeah, there's a flag for that. Didn't I put that flag in? Yeah, clone fs, clone vm, clone files, clone cgan, clone parent, clone thread, clone. What am I re-verifying? I don't want to re-verify anything, actually. And blah blah blah. IO. Am I cloning IO? That's what I should be cloning. Oh fuck! I do clone IO. It just wasn't there on the same line. The process shares an IO context with the calling context. Yeah. Maybe just shouldn't clone. Maybe we shouldn't. You know. Maybe we shouldn't clone IO. It doesn't work. All right, that's fine. I'd not thought of that. Who had? Okay, well, the thing is, it does work to child exit. Oh, exit child? Is that what it's called? Exit child. All the children will exit eventually. Fuck you. Okay. Eventually, one of the children was our guy. That makes sense. Yeah, that makes sense that it took that long as well. Okay. So it does happen eventually, and it does happen. So then in that case, jump if equal xmm12. Well, okay, first of all, xmm12 is the T. Spill the tea. Spill the tea. So really, U commas is for scalars, right? Scalar compares to scalar, single precision floating point values, which is what we want, yeah. U commas. And then xmm12. Yeah, so we're moving into xmm12. Maybe we shouldn't move APS, maybe we should just move SS. You know what I mean? Okay, no. let's just do that as well. No intersection. Oh, this is interesting too. Oh, my God, okay. I didn't ever change that. Alright, that still doesn't work, but that's okay. Okay, so let's get rid of that as well. Okay. Okay, so, track the closest, so that's happening. We want Yukamish. Alright, let's think through this again. We're testing the intersection. We don't care if the near... Okay, I did the wrong thing here. There it is. Okay. Okay, there it is. So there's only one cube. But that might make sense. One is actually quite a long way away. Seeing as the cube's only 0.5 by 0.5. So let's do V4 1. Let's add V4, what is it? Box max. And yeah. Okay, interesting. Very interesting. So it's now currently only thinking that it's intersecting with the second box, and it's also having a weird glitch over there. Oh, okay. Well, first of all, okay. One thing is, we should only be subtracting box max as well. Yeah, fuck off. All right, so it's only touching the intersection with the first guy. Okay, so the ignore. Are we doing this thing correctly? Is that what we just changed? I think it is. If our T near is less than closest. Oh no, we don't. No, it should be if it's above. Update. Yeah, rock his head in the sand denial. Just goes. This is correct. I think you're absolutely correct about this. What time is it? My God. Oh my God, it's 1:17. That's crazy. I gotta get out of here, actually. Which is too bad. Okay, well, interesting. Well, I suppose if I don't add this here, then this ends up being offset like the other one, right? Oh, well, never mind. Whatever. T near is less than T closest, up to T closest. interesting. Yeah, well, we do know that this is working, that the actual intersection math is working, because we just saw it working. Is anything updated throughout this process that we cannot have changed? That's probably what it is. Something on this first pass. I'm gonna write that as it should do. To check if something in this pass is changing which we need for subsequent intersection math is correct. We've seen it offset just fine. If t near results in a cube that's actually, yeah, that's weird, I guess. That is what it is? Yeah. We're ending the intersection early without updating the near. Yeah. I got to get out of here. I gotta leave. So thanks for stopping by, buddy. I hope that you have a pretty good day, and that it's got some real, I guess, I don't know, what do you call it? Some real chutzpah in store for you. I hope that everything that happens to you from, I guess, from here all the way up until you die, is just horrible.